Hi, welcome to my 142W capstone project presentation. My name is Louis Lin, and my presentation is on comparative analysis of V-type and inline engine designs. I'll be discussing each type of engine and some of their unique properties, showing that these engines are engineered through elegant physics and mechanics rather than arbitrary choices. So what's the motivation to discuss this topic? The motivation is to understand more about engines. Engines are an important part of our everyday life now. And for our commuters who drive to school every day, our packages, food to be delivered here through various different transportations, have we ever thought about what's really powering our vehicles under the hood? Most of us just get in the car and drive, but what about the engine, the heart of a car? What are some different designs of engines? And what are these difference? Any pros and cons? Any trade-offs? That leads to the discussion of today. In my capstone project, I investigate three main questions. First, how do different engines balance? Second, efficiency and performance of these engines. And lastly, for different type of engines, what are their different applications? So let's talk a bit more about engines. An engine is a machine that converts mechanical energy into work. It operates under four main stages to complete a cycle. On the right-hand side, we can see an animation of a working engine. At first, it goes to the stage of intake, which holds down the fuel to the chamber and then pushes up to compress the fuel, where a spark plug ignites the fuel within the chamber. It then pushes back the piston and it rotates back up to push out the gas. And during this process, the pistons are doing linear motion up and down, where a crankshaft is responsible for converting linear motion of the piston into a rotating motion, which then feeds to the wheel to power the vehicle. Now we have some basic knowledge of the engine. Let's go into the two different types of engine. First, let's talk about inline engines. So the name, why do we call it inline? It is because all the cylinders are arranged along the same line. So literally in the same line. In this engine structure, the pistons move along the same axis, simply up and down. It has a rather simple structure where a crankshaft connects all the pistons moving along the same plane. However, due to the geometry of the arrangement, it has a long engine length, meaning to add more cylinders, it requires more room. For inline engines, it could have an even or odd number of cylinders through modifying the crankshaft, which could still give us a complete piston cycles to provide power. Now for V-type engines. It's called V-type because it had a shape of the letter V. In this engine design, the pistons are split into two banks at an angle, typically 60-degree or 90-degree, depending on the specific engine design. The engine structure is symmetrical and it's more complicated because the pistons are no longer moving along the same plane. Yet, they're split into particular angles, making the engine design more compact, which requires less physical capacity for more cylinders. For a V6 engine like this, has similar length as an inline-4 engine from the previous slide. The V-type engine requires even number of cylinders to satisfy the structural symmetry. Now let's talk about engine balance for inline engines. Let's take inline 4, for instance. As shown in the diagram, there's a primary force component where the pistons are going up and down, labeled in green arrow, and the secondary forces are pushing up, labeled in red arrow, or down, labeled in purple, depending on the motion of pistons. These uneven accelerations are coming from the cylinders. Based on the geometry of the connection rod, they travel differently. The path lanes as the pistons approach the top of the cylinder versus the bottom are different, demonstrating in a figure. The orange part is the piston trajectory moving towards the top and coming back down, versus the blue line showing the piston trajectory traveling to the bottom. We could see that the orange line is shorter than the blue line, meaning that the piston speed changes from going upwards, slow down to zero, and coming back down in a short path, which correspond to the change in speed, acceleration to be higher. However, as the pistons travel towards the bottom, the change in speed is gradual. It had more time to slow down to zero and coming back up, meaning the acceleration is small. These accelerations are corresponding to the secondary forces of the piston within the engine. As we can see, the primary forces cancel out. However, the secondary forces don't cancel out to zero, results in a net secondary force within the system, causing imbalance through vibration. On the other hand, for the V-type engine, we see the symmetry based on the engine shape in a diagram. It shows the pistons pushing outward, labeling green arrow, and inward with orange arrow in the engine. Forces on the horizontal axis cancel out, and on the vertical axis, based on the geometry of the engine and the angle, the forces partially cancel. And for the purpose of demonstration, we can neglect such small variation. In terms of efficiency and performance, an inline engine has a simple system structure with a single cylinder bank, meaning less components involved and fewer friction sources, resulting in less energy loss within the mechanical system, which is more efficient. However, there are trade-offs. Since the structure is relatively long, adding more cylinders increases the engine size, which limits the amount of cylinders we could put in this engine. And that sets a limit to the amount of power we could generate from the limited space in the engine hood. Also, there's an imbalance caused by the engine vibration generated from the secondary forces, responsible for some energy waste. One example for inline engine is a BMW X3, which is a medium-sized SUV. For a V-type engine, it has more complex engine system, increases the number of moving components inside, and leads to a higher friction. Since there are more cylinders, more energy conversion takes place, making it heats up more and has a higher thermal dissipation. The engine tends to have a higher fuel consumption, reducing the overall efficiency. This engine is good for performance. More cylinders can be put in the engine, allowing higher power output without increasing much of the engine size. Meanwhile, the arrangement of the cylinders allow the force to be canceled more effectively, reduce the system vibration, make it smoother with less energy loss. An example for the V-type engine is a Audi S6, which is a high-performance sports car. Engine applications. For different types of engine or design, they serve a different purpose. For inline engines, it's commonly used in economy cars and compact vehicles because they have a simple design and high fuel efficiency. No one wants to pay $100 every week to fill their gas tank. So this is ideal for daily driving. It's also commonly used for small motorcycles in which the inline configuration can be a great fit due to their simple and lightweighted design. The inline engine are mostly used for light duty due to the power limitation. And for V-type engines, They're commonly used for sports cars because their higher power limit allows larger acceleration and higher speed. It is very common use for high performance sport vehicles. The engine designs for higher power rather than fuel efficiency. And it's and it's also commonly used for large SUVs, trucks, and heavy-duty vehicles because they could output larger torque, which is essential for carrying larger number of passengers or carrying heavy cargo. The comparison between these two types of engines have well demonstrated the uniqueness of each design, the purpose, and strong suit each type holds. These engine designs showcase the beauty of creativity, combining magnificent engineering and elegant physics. That concludes my presentation for the capstone project. Thank you all very much for your time and patience. Hope you all enjoyed this presentation and learned something from it. Again, thank you very much, and until next time.